In this lesson, we will look at ways to optimize the injection control settings for the molding process. These settings include fill rate profiles, transfer set points, packing and holding controls, and mold open and close timers. We will describe rules and procedures for setting and maintaining each of these controls. Molding machines that use a closed-loop fill rate control will have a maximum or limiting injection pressure setting. This is the maximum injection pressure available when the fill rate control system operates during mold filling. The general rule for setting this pressure is to set it high enough to meet the pressure demands of the fill rate control system, but not so high that the mold could be damaged if this pressure remains on after the mold is full. If the cavity filling resistance increases, the machine requires more hydraulic injection pressure to fill the cavity at the set rate. If the asked for pressure is higher than the maximum pressure setting, an alarm will be triggered to alert you to the problem. You may have to lower the fill rates or raise the maximum injection pressure setting to fix the problem. On molding machines without fill rate control, mold filling and packing is done by using a single injection pressure, often called the first stage pressure. Because this is a single pressure, the fill rate decreases as the flow resistance increases. Therefore, fill rates are not controlled. Fill rate controlled machines have several fill rate settings. This control is commonly called boost, injection, or velocity profile. The general rule for mold filling is to fill the mold as quickly as possible. Fast filling reduces the amount of plastic cooling by the mold during filling, and it also reduces the cycle time. Thin parts are nearly always filled quickly to reduce plastic cooling during fill. Thick-walled parts are sometimes filled slowly to reduce molded-in stress. However, extremes of either very fast or very slow filling result in higher stress. Some situations may require fill rate adjustments. For example, jetting is caused by plastic squirting through the gate and not forming a flow front at the start of mold filling. One solution to jetting is to reduce the initial fill rate to create a flow front as the plastic leaves the gate. Flash can be caused by either a high filling pressure or a high packing pressure. If a high filling pressure causes flash, this pressure can be reduced by reducing the final fill rate. Burn marks can be reduced or eliminated by slowing the final fill rate. This allows more time for air to escape from the mold. Fill rate control is also used to change stress, orientation, and weld lines in particular regions of a molded part. This is a trial and error procedure in which the plastic flow rate is changed as the plastic first passes through a critical area of the part. Insert molding often requires that the fill rate control system be used to reduce the force of the flowing plastic against the inserts so they are not moved out of alignment during mold filling. A word about terminology. We use the terms packing and holding pressures to describe different phases in the molding cycle. We use packing pressure to describe the part of cavity filling where the cavity pressure is raised to its peak. We use the term holding pressure to describe how part properties are manipulated by maintaining or decaying the plastic pressure in the cavity until the gates freeze. Molding machine makers use different terminology on their controllers to describe these phases and pressures during a molding cycle. For example, many controllers use terms like holding pressure profile or hold profile to describe the pressure settings that both pack and hold pressure on the cavity. So that when you set a holding pressure profile on the controller, you're really setting the packing and the holding profile. Be sure you understand the terminology your machine controller uses and how it relates to the packing and holding terms we use in this course. The setting of the transfer, or cutoff point, is a very critical setting. It determines when the machine shifts from controlling the fill rate to controlling packing and holding pressure. Because the hydraulic valves take from 20 to 100 milliseconds to operate, the transfer point is usually set to occur just before the mold is full, typically at 95 to 99% full. During the delayed hydraulic valve response, the cavity completes filling. To find the correct cutoff point from fill rate control to packing control, you should follow a prescribed procedure. Here is one suggested procedure. This procedure should be used only if your mold can eject a short shot. You begin by setting the transfer point typically a ½ inch, about a centimeter from screw bottoming. Part of this distance will remain as the cushion, and part will be additional plastic packed into the mold. Larger screws and molds require a larger cushion. Smaller screws require less. Set the packing and holding pressures to 0 so that they do not cause plastic flow after the transfer point is reached. The next step is to find the best stopping position for the screw during screw recovery. The proper setting will be the position that results in a shot volume that, when injected into the mold, produces parts that are just slightly short. Cycle the machine adjusting the screw stopping point each cycle, until you find the shot volume that fills the mold 95 to 99%. On thinner parts, this point may appear as a very slight short shot. On thicker-walled parts, the part may appear full, but might have pronounced sink marks. Different parts will exhibit different characteristics, but the key is to experiment enough with the shot size to determine this point. This is the optimum screw stopping point. After the transfer point is set, the controls to pack and hold pressures on the plastic can be set. To control the packing of the cavities, several different techniques are used depending on the capability of the molding machine and the desired part properties. But the goal of all packing techniques is to achieve a consistent peak cavity pressure that produces a part with the desired characteristics. One packing method is to use a pressure and a timer setting. In this method, a set pressure is held for a set length of time. This graph illustrates the technique. After the cutoff point is reached, the machine switches to controlling pressure. In this case, it holds 1500 psi, that's hydraulic pressure, for ½ a second. Sometimes more than one packing pressure is used. Here we've added a second packing pressure of 1700 psi for1/4 of a second. Note that the transition from the cutoff point to the first pressure setting and from the first pressure setting to the second pressure setting is abrupt. The hydraulic controllers on some machines ramp the pressure used for packing. Ramping allows the set packing pressure to be reached over time. For example, if we set a ramp time of a ½ second, it will take ½ a second for the pressure to reach the pack pressure setting. The advantage to using the ramping capabilities of your controller is that it smooths out the pressure curve of cavity packing, resulting in more uniform and consistent part characteristics. Another method of controlling packing in the cavity is packing at a fixed rate by controlling the packing velocity. In this method, at the mold full point, the cavity is then packed at a constant rate. The control system maintains a set packing rate by using whatever injection pressure is needed, up to the maximum injection pressure setting. If the maximum injection pressure is reached, however, there will be a loss of control since process adjustability is no longer available. Packing is ended when a preset cavity pressure is reached. Another method of cavity packing uses the cavity pressure as an input. If a cavity pressure transducer is installed in the mold, the packing rate and pressure can be more accurately controlled. Through experimentation, the ideal cavity packing pressure curve is found. This curve reflects the packing rate and pressures that produce parts with the desired properties. Using this cavity packing profile as its input, the control system adjusts packing rates and pressures as necessary to replicate the curve each cycle. This is a sophisticated and accurate means of controlling cavity packing. In summary, regardless of the packing method that's used, the objective is the same. It is to force additional plastic into the cavities to achieve the desired peak cavity pressure. This compensates for the shrinkage that occurs when the plastic cools, and does it in such a way that the required part properties are achieved. After the mold is packed, one or more additional holding pressures are set to either maintain or decay the plastic pressure in the cavity until the gates freeze. These holding pressures are the final pressure adjustment the molder can make to change part properties. The amount of holding pressure affects the internal part structure, part appearance, and the final part dimensions. A high pressure puts more plastic in the cavity and results in less part shrinkage, fewer sink marks, and less voids. Too high a pressure can cause overpacking of the cavities and high internal stresses, which can lead to cracking. It can also result in the parts not ejecting easily or even sticking in the mold. Holding pressure settings can be different for crystalline versus amorphous plastics. Amorphous plastics are more prone to overpacking in the cavity due to their molecular structure. A decaying holding pressure profile can be used to avoid this. Crystalline plastics often make better parts if the holding pressure is held high while the crystalline structure is formed. This enhances dimension control and promotes a uniform crystalline structure. After the crystals freeze, the holding pressure can be reduced fairly quickly. The molder should only use as much holding pressure as necessary to achieve the part appearance and dimensions. The holding timers set the amount of time each holding pressure stays on. After the gates freeze, the holding pressure no longer has any effect on the molded parts. A holding timer set for longer than it takes the gates to freeze wastes energy and causes unnecessary wear on the pumps and valves. You can determine the correct setting for the holding time by determining when the gates freeze. This can be done by measuring the part weight. Start by setting the holding timer longer than it takes the gates to freeze. Then, after each cycle, shorten the holding time by about half a second. Accurately weigh the molded part. When the part weight begins to drop off, it means the holding time is insufficient to allow the gates to freeze and discharge occurs. The proper holding time should be set a second or two longer than that. If cracking at the gate region is a problem, it can be minimized by a controlled pressure release of the holding pressure shortly before the gate freezes, so as not to overpack and overstress the gate area. Another technique is to reduce the holding time so that a small amount of plastic escapes from the gate area when the holding pressure is released. This will also reduce the stress in the gate region. The mold closed, or cooling time, is usually the longest phase of the molding cycle. Cooling time is minimized by using good molding techniques. First, you should experiment to determine the lowest melt temperature that will make good parts. The less heat you put in the plastic, the less heat you have to take out. Lower mold temperatures also help reduce cooling time. But low mold temperatures increase the amount of injection pressure required to fill the mold and may also cause undesirable part properties like stress. The general rule when setting the cooling time is to use the minimum time necessary to make good parts. To find the minimum cooling time required to make good parts requires experimentation. Don't assume you are running the minimum cooling time just because your parts meet QC specifications. It may be possible to reduce the cooling time and still make good parts. Because cooling time is the longest part of the molding cycle, it offers the most opportunity for cycle time reductions, and therefore increased efficiency and profitability. The time between cycles, that is, the mold open time, must also be controlled. When operating in the automatic mode without an operator, the setting for the mold open time should be the minimum that allows enough time for the parts to eject. When operating in the semi-automatic mode, the mold open time is controlled by the opening and closing of the safety gate by the operator. It should be kept consistent. To maintain consistency, it is a good idea to still use the mold open timer and set it for slightly longer than it takes the operator to open and close the safety gate. The general rule is to minimize the mold open time and keep it consistent. While small variations in the mold open time may have only a small effect on the melt temperature and the mold temperature, the goal is to eliminate all unnecessary variations in the process. In this lesson, we've described rules and procedures for setting and maintaining the injection control settings, fill rate profiles, transfer set points, packing and holding controls, and mold open and close timers. Making control adjustments and changing processing conditions will have an effect on molded part properties. But remember, these are general procedures, and in all cases you must follow the specific operating procedures for your molding process as published by the equipment manufacturers and as given to you by your own plant management.